This one is going to be a quick corollary to the theorem about composition in the previous video. So let's suppose you have two measurable spaces x and y and a measurable function f from x to y. So we're assuming it's a measurable function. And let's say you have a subset E of x. So E is a subset of the domain, and so you can restrict f to E, right? And if you do that, then that will also be a function from E also to y, right? What about this function? Can we say that this is a measurable function in some sense? Well, it's definitely not an A-B measurable function. That wouldn't make any sense because A is not a sigma algebra on E. It's a sigma algebra on X, right? But we have a way of talking about a sigma algebra on E that's related. And we have two ways of describing it, actually. So the idea is take the inclusion map from E to X, which is basically just the identity function on E, except we enlarge the codomain and allow it to be X. So take this inclusion map, then you've got sort of A, your sigma algebra on X. You can pull that back to get a sigma algebra on E. So you could use this sigma algebra for E. Then we can ask, is f restricted to E a measurable function in the sense of using this sigma algebra for E and this sigma algebra B for Y? And this corollary says yes. So then f restricted to E is pullback of A, comma, script B, measurable. And remember, this pullback of A thing is not such a complicated thing. It just ends up being, it's the collection of preimages under the inclusion of all the things in script A, right? But when you take a preimage under the inclusion, you're just intersecting with E. So it's just taking the sigma algebra on X and then intersecting all of the measurable sets with E. So here's the proof of the corollary. F restricted to E is actually just F composed with the inclusion, right, where I is the inclusion map. So F restricted to E is this composite. First go from E to X, then go from X to Y. Here use F, and here use the inclusion map. And so this is a composite of measurable functions. But hang on, F is measurable by assumption. Is I measurable? Is I measurable? So here's a way of describing the question, is I measurable or not? For I to be measurable, we need it to be that if I take I and I pull back the sigma algebra on X, we need that to be a subset of whatever is the sigma algebra I'm using for E. But what sigma algebra am I choosing to use for E? Is this itself, right? The pullback of A. So yeah, I is measurable by the choice of sigma algebra we put on E. We chose the sigma algebra on E so that it's pretty much the smallest sigma algebra you could put on E that would make I be a measurable function. So this composite is measurable by theorem 2.1 L2, the one in the previous video.